What are thermal treatments? Why do they apply to sewage sludge? Let's start with a brief overview. Some thermal treatments of sewage sludge, like drying, are usually carried out at temperatures ranging between 70 and 150 degrees Celsius and involve no chemical transformation. Most processes are carried out at medium-high temperatures, from 150 to more than 1000 degrees Celsius. They involve chemical transformation and are more properly called thermochemical processes, such as combustion, gasification, and pyrolysis. More recently, other thermochemical processes have been developed, such as thermal liquefaction processes, hydrothermal carbonization or dewatering, thermal hydrolysis, and others. Thermochemical processes can be endothermic, requiring heat to be carried out, exothermic, producing heat, or even autothermal, which means with no uptake nor release of heat. Therefore, they are typically carried out at different temperatures. Combustion is the hottest process from slightly less to more than 1000 degrees Celsius. Gasification can range from 600 up to 1300 degrees Celsius, whereas pyrolysis is typically carried out below 800 degrees Celsius. They, of course, differ also for the outcome of the process in terms of type and amounts of products. Whilst combustion releases heat, flue gas, and ash, other processes feature a more various mix of products: synthetic gas, pyro oil or bio-oil, char or biochar or hydrochar, and so on. Some of these products can be potentially valuable from the points of view of both the recovery of energy and the recovery of materials. However, a crucial point that needs to be considered with care concerns the energy balance of these processes. Since sewage sludge, as produced by wastewater treatment plants, is rich in water and very poor in energy content, most of the thermochemical processes require a first treatment to remove part of the water by dewatering or drying before undergoing these processes. Decreasing sludge moisture increases its energy content. Conversely, if the moisture of sludge is too high, the heat required to evaporate the excessive moisture entails the need of adding external energy to sustain the process. Therefore, why do thermochemical processes apply to sewage sludge? First, because these processes kill all the pathogens and in most cases destroy most, if not all, the biological matter that can sustain the life of microorganisms. Moreover, higher the temperature, lower the number and the complexity of the chemical species produced by the process. Having to deal with a limited number of chemical species is a very relevant advantage in preventing pollution. Second, they reduce considerably the amount of solid residue to be handled. Third, they concentrate some valuable elements like phosphorus into this reduced amount of solid residue, opening the possibility for recovery processes. Currently, the most widespread thermochemical process applied to sludge is combustion. Combustion of only sludge is called monocombustion, whereas the combustion of sludge together with other materials, typically other solid waste in waste incinerators or other fuels in cement kilns, is named co-combustion. On the one hand, co-combustion is carried out in large facilities equipped with cutting-edge pollution control systems, warranting very high environmental performances. On the other hand, monocombustion produces ash coming only from sludge. Such ash is not diluted with the ash coming from solid waste, and neither is lost in the cement product, as it happens in cement kilns. Therefore, ash from monocombustion features the highest concentrations of valuable elements and is the best candidate for phosphorus recovery.
What to say about material recovery from thermal treatments? As previously mentioned, monocombustion of sludge produces ash. The interesting point is that this ash contains from 7 to 8% phosphorus by weight. Phosphate rocks are among the critical raw materials, and to cope with its increasing scarcity, the European Union promotes the recycling of materials containing phosphorus. When sludge cannot be used in agriculture because of legal restrictions, we can recover its phosphate content from sludge ash. During the last 10 years, several techniques have been developed and tested at pilot scale and also at a larger scale in demonstration plants. You can find a full list in a document issued by the European Sustainable Phosphorus Platform. Of the many processes, wet acid extraction techniques proved to be the most convenient and feasible so far. As a matter of fact, the first full-scale plant designed to recover phosphorus from ash is being built in Schkopau, Germany, and it will treat 30,000 tons of sewage sludge ash per year. Other thermochemical techniques do not allow to recover much energy, but, on the other hand, they have the advantage to allow the recovery of carbon and nutrients such as nitrogen and phosphorus. It is worth mentioning one of these processes, called hydrothermal carbonization, or HTC, as it counts some full-scale plants treating wood, organic fraction of urban wastes, but recently also sewage sludge. HTC produces a slurry which can be separated into a liquid fraction rich in biodegradable organics and into a solid fraction called hydrochar rich in carbon and phosphorus. Regulations about the possible uses of this material are still under evaluation by authorities. Hydrochar may be used as a solid biofuel or as a soil improver. Potentially, it may be also used in the production of activated carbon or even of catalysts and carbon-based electrodes. Phosphorus can be recovered from hydrochar with similar extraction efficiency values, PEE, to those of incinerated sewage sludge ash, ranging from 55 to over 90% of the content in sludge. Last but not least, the recovered P product can be refined to serve for many purposes, not only for manufacturing fertilizers, but also as animal feed integrator, additive for fire extinguishers, and other industrial uses. The inert residual left after phosphorus recovery can potentially be used as inert material in the construction sector, for example in cement kilns or to make stoneware tiles. Then I can close by saying that thermochemical processes really contribute to closing the cycle of the water sector, producing almost no waste residues from wastewater treatment.